Good morning, students. Myself, Vijay Shankar from BC Department, Chevrolet Engineering College. Today, we are going to discuss about the examples in this linear system. We already learned in the last class examples of linear and nonlinear, and time variant and time invariant. These are the two properties we have. And the third property is a stable and unstable system. And fourth is a non-causal and the causal systems. Let us see the examples of stable and unstable and causal and the non-causal systems. Stable system. Stability, the system is absolutely integrable, or for every bounded input, there is a bounded output. For the given function, can apply the integral with respect to the time. If the signal is a time domain, its value is must and should is a finite value, nothing but it is a less than the infinite, that the system is a stable system. Simply any system, any function we can give, can apply the integral, and that integral is absolutely integrable, nothing but it will get the finite value. It is a stable system. Otherwise, it is an unstable system. Okay. Causal and non-causal means a system is causal if it output y of t naught depends upon only on the values of the input x of t at t is less than the t naught. T is less than the t naught means it depends upon the t and the past inputs, the present and the past inputs only. It does not depend upon the future input. The system is said to be non-causal system, which output depends upon the feature values of the input, that is the feature inputs and the outputs. Okay, so the y of t is equal to x of t minus 1. X of t is the present input, means x of t minus 1 is the past input. It depends upon the present or the past or past inputs and the outputs also. The x of 2 minus 1, x of 2, because the y of 2 is there, x of t is a present input, x of 2 minus 1 is past input. The y of t, the x of t is a present input, x of t minus 1 is a past input. Y of 2 means x of 2 is a present input, x of 1 is a past input. Okay, so the output function y of t depends upon the only the values of the inputs t is less than the t naught. Less than or equal to also you can say. So x of t is equal to 0 for less than the t 0, and nominal for the t is less than or equal to the 0. The system is said to be the non-causal if the output depends upon the feature values of the input, feature inputs and the outputs. See the y of t means x of t is a present state and x of t plus 1 is a future input. So it is a non-causal system. Y of 2. Y of 2 means the present input is x of 2. X of 3 is a future input. So the x of 3, the function is depends upon the x of 3. It depends upon the future input, then the system is a non-causal system. See the examples. The y of t is equal to k into x of t plus 1 and x of t. So the t is a present state, x of t is a present input, but x of t plus 1 is not the present past inputs or the present input, it's a future input. So system is a non-causal system. Second example, 3 into x of t plus 3. So y of t, in that y of t, the t is the present input means it is depends upon the x of t or the below the values of x of t, the t minus 1 or the t minus 2, but the t plus 3 is a non-causal system. Okay, the y of t is equal to t plus 3 x of t minus 3. T plus 3 is not the signal, it's a scaling factor only. Okay, the ramp function x of t minus 3. X of t minus 3 means t is the present input, x of t minus 3 is the past. So it depends upon the present inputs and the past inputs means that the system is causal system. What it matters. And similarly, the y of t is equal to 2 into t. So y of t is equal to x of 2 into t. Means that t is the present state. Let us take the 0 is a 1. Definitely it becomes x of 0 is a causal only. X of 1. When if I take the 1, the x of 2 means it depends upon the past feature input. So from 1, 2, 3 for the values, it depends upon the feature inputs. So it's a non-causal system. Got it, Martin? And y of t is equal to x of t plus the integral 0 to t x lambda into d lambda. X lambda into d lambda. So it is also the causal system when we can substitute the t is equal to 0, 1, 2 means the x of t plus is the z of lambda, the causal system of it. It depends upon the present and the past inputs. And the fourth example, you can see the x of y of t is equal to x of t plus 3 into x of t plus something is there. Definitely, if it is a plus value means advanced function, it depends upon the feature inputs only. Then the system is a non-causal system. Definitely. Okay. And the y of t is equal to x of t square. X of t square means when the t is equal to 0, definitely the y of t is equal to 0. Y of 0 is equal to x of 0. It's a causal only. It's a present input. And t is equal to 1. Y of 1 is equal to x of 1. It is also present input. When t is equal to 2, t is equal to 2 means x of 4. So y of 2 is equal to x of 4 means it depends upon the feature input. Let us take the minus 1. T is equal to minus 1 means y of minus 1 becomes a 1. It is also the feature input. So the total function, only the t is equal to 0 and t is equal to 1. It depends upon the present. So it is a causal only. But when we take the minus 1, 2 also, it depends upon the feature inputs. So totally, the system is a non-causal system except at t is equal to 0 and t is equal to 1. Okay. And in this function also, the except t is equal to 1 and the t is equal to 0, t is equal to 2, it is a causal. Except that t is equal to 0, t is equal to 1, the response of any function that depends upon the feature inputs. What it matters, students? Okay, stable means any given function, apply the integral, and that integral is absolutely integrable less than the infinite. The finite value will get that system is a stable system. Otherwise, it is a unstable system. Causal means it depends upon the present and the past inputs. Then the system is causal. If it depends upon the future input, then that system is a non-causal system. Understood, madam? So the four properties we discussed with examples yesterday class and in the today's class up to. And now go for the next one is the impulse response, the frequency response. First of all, what is the impulse response? Impulse response means it's output only. H of t. Response is h of t. For which signal will get the impulse response? For the impulse signal. What is that impulse signal? Delta of t. If delta of t passes through the linear time invariant system, already we discussed linear system and the time invariant system. Combining linear time invariant system, the h of t is equal to is a function of delta of t. If the input is the impulse signal, which passes to the system, we get the response. That response is the impulse response on the impulse signal. On the impulse signal, we'll get the impulse response. Okay, every system is categorized by its impulse response. H of t. In general, we are representing the h of t. Okay, if the response is delta of t is h of t, the delta t minus t naught is also delayed. H of t minus t naught, nothing but it is a linear time invariant system. So x of t, combine the x delta of t and delta of t minus t, h of t plus h of t minus t naught. The response of the system for a given input f of t is determined by using the superposition principle. The step 1, step 2, and step 3. First of all, the first step 1 is resolve the input function in terms of the impulse function. Determine individually the response of a linear time invariant system for impulse function. Third step is find the sum of the individual responses, which will become overall response R of t. Overall response R of t. Got it, my dear students? So the response of the system for any arbitrary input, that response is the impulse response. They individually can find out, resolve the input function in terms of the impulse function. Determine individually the response of linear time invariant for impulse function. Individually. Find the sum of individual responses will become the overall response of the R of t. Okay, whenever you can consider as input is f of t and output is a R of t, in the linear time invariant system is representing with the h of t. Got it, my dear students? But the convolution between the two functions f of t with the convolution of the h of t. Okay, so representation of a function f of t in terms of the impulse function, the first step. See, we will learn in the sampling also, the function x of t is combined with the impulse functions or the impulse train. Here the function f of t is the impulse train function. One is the delta of t, next is a 2 delta t, 3 delta t, 4 delta t, and 5 delta t. The gap is where here. Delta t, the relation to 0 delta t, 2 delta t, 3 delta t, and so on. Okay. The area is f of t is equal to sum of n is equal to minus infinite to infinite. The function n into delta of t, n into delta of t, where n is varies from the 0, 1 to 3, and so on. What it matters to us. That is a representation of the function f of t in terms of the impulse function. Step 1. And that is multiplied, the f of t is equal to the delta t tends to sum of n is equal to minus infinite to infinite, f of n into delta of t. And even if it is a multiplied with the delta of n minus n into delta of t, the value is a unknown impulse response. Okay. And second step, determination of R of t from the input f of t. Let the h of t the impulse response of the system with the impulse function delta of t. To get the response is h of t. If this delta impulse signal is delayed with the t minus n into t delta t, the output is also delayed. It's a linear time invariant system. H of t minus delta n into, not the delta, n into delta of t. Then after, this total function is multiplied with the f of n into delta of t. We'll get the f of n into delta of t, and the delta of t function also multiplied on both sides, f of n into delta of t, delta t, and the delta of t minus n into delta t, and is equal to, or is equal to, it passes through the system, you get the response with the impulse signal. Why I'm saying it is a R of t, here the t is there. Whenever the t is multiplied, the t function is R of t. The ramp signal, simply saying. Okay. Apply the summation on both sides and take the delta, limit to delta tends to 0. The response will get as the f of t with the input and the system, it passes the R of t. Here the delta t is there. As delta t tends to 0 means the summation becomes an integration. The R of t is equal to integral minus infinite to infinite f of tau h of t minus tau beta. Okay, the integration you can apply as take the n into delta of t, n into delta of t as a tau function is becomes of f of tau h of t minus tau beta. Okay, that I told that the relation between here the f of t and the h of t system is nothing but h of t. Input function is f of t. Getting the response is r of t. So r of t is equal to the convolution between f of t and the h of t. So now what is the formula for the integral minus infinite to infinite f of tau and h of t minus tau deta. Okay, the same function we got. So r of t is equal to the function f of t with the convolution of h of t. F of t is the input and h of t is a linear time invariant function. To get the response is a ramp function. Okay, r of t. In the frequency domain, the r of t is r of omega and f of t is f of omega and h of t is h of omega. We know that is one of the property. Convolution in time, x of t with the convolution of not the x here, the ef of t with the convolution of h of t. Apply the Fourier transformation on both sides, it becomes of f of omega into h of omega. Okay, my dear students. So always we are checking that is a x is a input function, or otherwise there would confusion whatever we wrote here. F of t is f of omega, h of t is h of omega. Okay, and this is equal to the r of t. Okay, r of t is equal. So r of omega is equal to, in the frequency domain, the f of omega into h of omega. So what is the h of omega? Impulse response is h of t. Impulse response, you can call it as impulse response. Remember, very good. Impulse response, and the delta of t is the impulse signal. Impulse signal. Now we got the frequency response. H of omega is equal to r of omega by output by the input f of omega as a transfer function, or is also called as a frequency response. Frequency response. What it matters first? When f of omega is equal to 1, that is the input is a unit impulse, h of omega is equal to r of omega. Input is a unit impulse because it's the input is a delta of t. You'll get the h of omega is equal to r of omega more. The delta function is always a 1. Even if it is a shifted also, you'll get only the 1 back. The transfer function h of omega of a system is defined as the transform of the response of a system where the input is impulse unit function or unit impulse function. You take that as having the h of omega is equal to, having the magnitude is h of omega and the phase angle is e power j into theta of omega, where magnitude of h of omega is the amplitude response of the system and theta of omega is a phase response of the system. Amplitude response of the system, and it is a phase response of the system. Okay, my dear students. And inverse Laplace transformation will get h of omega is equal to the gain of the system L of omega, and it is in the complex function. You can write this function as a complex function. L of omega plus j into theta of omega, the gain of the system and the phase shift introduced by the system. Got it, my dear students? What is the impulse signal and how we'll get the impulse response when it is passes to the system? That impulse response will take as a system, the linear time invariant system with a function of f of t. Getting the response is r of t. R of t is equal to the convolution between h of t and the f of t, and then we'll get the frequency response. H of omega is equal to r of omega by the f of omega. Got it? An impulse function contains all frequency in equal amount, so we can use it as a test function. H of omega is equal to r of omega by f of omega is a transfer function of linear time invariant system. So Fourier transformation of h of t is h of omega, and h of t is equal to inverse Fourier transformation of h of omega. Got it, my students? And the filter characteristics we already discussed in the last before the two classes. So let us again, we can see the ideal and low pass filter. It transmits all the signals below a certain frequency of beta hertz without any distortion. Okay, means it allows only the low frequency value from beta b hertz, and with the symmetry, if we can take as a minus b to the b as a rectangle function, we can call it as a pass band, and the remaining part, whatever it is, we have stop band, and here also the stop band. Okay, it transmits all the signals below certain the frequency b hertz without any distortion. The range of frequencies from 0 to beta b hertz is called pass band of the low pass filter, 0 to b. The frequency b hertz is called cutoff frequency of an ideal low pass filter. It's called as a characteristics is ideal low pass. Practical low pass filter is there is some transition band. Slowly it is decreases, not the suddenly it is decreases to the 0. So the transfer function of ideal low pass filter is written as h of f is equal to some k into e power minus j omega into t naught in the range of minus b to the b, and greater than the b, the value is a 0. Okay, my dear students. The transfer function is amplitude is a k, and it is an exponential function e power minus j omega in terms of the f 2 pi f into t naught. Where k is an amplitude is assumed with the unity, and when k is equal to 1, the h of f is equal to e power minus j 2 pi f into t naught in the range of minus b to the b, and 0 with the greater than the value stop band. By inverse Fourier transformation, h of t can be obtained as an ideal low pass filter. H of t is equal to integral minus b to the b. Here the h of f is e power minus j 2 pi f into t naught as a function of h of f. The h of t is equal to, actually the formula is a 1 by the 2 pi in terms of the angular frequency minus infinite to the infinite x of omega into, or the x of omega. Here I'm taking the h, means you have to take only the h here also. H of omega into e power plus j omega t into d omega. Now it converted to the normal frequency 1 by the 2 pi. The integral minus infinite to infinite. The shortcut notation of the 2 pi f is a f e power plus j 2 pi f into t, and d omega now we can write as a 2 pi f into df. In that case, the 2 pi get cancelled. So what is the h of f? We got you can substitute h of f as a e power minus j 2 pi f into t naught. And already we have the positive exponential. Apply the integral on both sides, not the both sides, integral with the exponential function. We'll get sine function 1 by t minus t naught, the sine after substituting the b value plus b and minus b. The sine function, sine pi theta by pi theta, we can write it as sinc theta. So sinc means it is always amplitude is goes on decreasing from 2b to the low value and towards positive T values and towards the negative T values also. Okay. The figure shows that the impulse response exists for negative values of T, but actually the unit impulse is applied at T is equal to 0 always. Practically, it is impossible to implement such a system. So ideal low pass filter, the practically is not realizable. Physically, it is not realizable. So we go for the another way. The another ideal low pass ideal filters such as high pass filter and the band pass filters. In realizability of ideal low pass filter, its response begins before the input is applied. Because why it is physically not realizable means before the input is applied, it gives a response. It begins the response, and hence it is not physically realizable. Similarly, the high pass filter, band pass filter, ideally have frequency response as shown in the figure. The high pass filter means it allows only the high frequencies, it does not allow the low frequencies. So the low frequency is the stop band, high frequency is the pass band. These have the sharp transition in the frequency response. All ideal filters are physically not realizable since the impulse response is non-causal. Impulse response is non-causal, means it is depends upon the feature inputs. Okay, physically not realizable all the ideal filters.